So today we're going to try to elucidate the mysteries of the TTL gate, like the gate that's in this beautiful 7400 TTL circuit from Texas Instruments, a fine example from 1973, because it's a really weird circuit. If you look at the TTL data book, this is edition 1 from 1971, prepare the page, and they give you the circuit of what makes this one tick. And it's this really weird circuit with a transistor with two emitters, and I had never found a convincing explanation of how it works. But today we're going to find out for ourselves, because I finally have a transistor with two emitters. That's the inch that we found in our Apollo PCM circuit that makes the multiplexer, and that we tried before for a completely different reason. But it is a transistor with two emitters, so this is exactly what the doctor ordered for us to experiment with a TTL gate. So in order to better understand the TTL gate, it's helpful to put it in context of what happened when in 1965, when Texas Instruments introduced the TTL gate. Here I should have said when Texas Instruments introduced their version of the TTL gate, as several other manufacturers had already started making them. The original patent is assigned to TRW, for example, and Sylvania had early devices. But TI's version was soon going to dominate the market and become the de facto standard. Here you go. So that's a copy of the 1965 catalog. New series 5400. So it started with the military series, and here's our TTL gate, and it's the same schematics as I just showed you. TTL stands for transistor logic. Why that? Well, if you look at the other page, you can see what other series they had before. They had DTL, diode transistor logic, where you have a bunch of diodes doing the ANDing or ORing function. This is similarly of military origins, made by North American Aviation for the Minuteman missile. And then here is another one, which is RTL, resistor transistor logic, manufactured to the full performance specification of a sponsoring government agency. Can you guess which government agency that is? So this is a gate I recognize. That's the one that was ordered for the Apollo guidance computer. It's a 4-input NOR gate. So eventually the 3-input was selected, but it's exactly the schematic. So this is ordered for missiles. This is ordered by NASA for the Apollo guidance computer. And then this one is for some military purpose before the non-military 7400 series is announced. So the emergence of ICs is all linked to military developments. So in order to better understand the evolution from DTL to TTL, I've made those little schematics here. So here's the original DTL gate. The way this works, if A and B are at a positive voltage, or actually not connected to anything, then the current comes through the resistor, through the diode, turns the transistor on, and this is at 0, because the transistor shorts it to ground. If either A or B or both are close to the ground, then this will be close to 0.6 volts, and this is actually through the two diode drops will become negative, and it will turn off the transistor. This comes back to 1. So this is how you implement an AND gate. Note that they use a negative voltage usually in DTL. That's for a side issue, because they never want D3 or D4 to stop conducting, so they don't have the penalty of the recovery. So instead they keep it conducting, but to a negative voltage, but we can ignore that. So I just converted this so it works out of a single voltage. So you see my 2-input diodes, I eliminated one of the diodes, so it is only 1 because I only grounded to 0 volt. I stuck it to the back of a TTL circuit, which is actually the same as here, except they put what's called a totem pole output to boost the fan out. So one output can drive a lot of inputs. one transistor to pull the logic high, and another transistor to pull the logic low so that the current can go either way fairly strongly. So it gives you a lot of fan out. You see that's an NP junction, and that's a PN junction. Huh, that looks like a transistor. And here's another NP junction. Oh, that looks like a transistor with two emitters. And that's of course exactly what they have done in the final TTL gate. And usually when people explain it, they say, well, this is equivalent to this, but we'll see that is not really true. There is a very good reason why they choose a transistor instead of using diodes, and it makes a world of a difference. So I'm going to build those two circuits with discrete components, and I will be helped by our friend the inch, which we described in another video because we found it in an Apollo circuit. And it was made for a totally different purpose, but if you look at the schematics, it's a transistor with 4 legs and 2 emitters, so that's exactly what we need. Although it wasn't meant to make TTL gate, we'll use it as such. So, helped by the inch on my breadboard, I have built those two gates. At the bottom is the DTL gate, and you can recognize the 2 input diodes. The diode that connects to the transistor, that's our switching transistor, and that's our totem pole output. The TTL gate is almost identical. The 3 transistors in this stage is exactly the same. All I have done is replace my DTL diode arrangement with an inch at the input. I drive it with 2 inputs, 1 megahertz signal. The original gate is at 10 megahertz, so I thought 1 megahertz would be a good place to start. And I'm ending it with something that's 200 kilohertz, 5 times as slow. I am monitoring the TTL gate in blue and the DTL gate in red. And when you look at it, well, the TTL gate is working a little bit. The TTL gate is not even there. Well, there are little blips. So let's slow down and see if we get somewhere. There we go. Now we have a good TTL gate, and the DTL is starting to come to life. Immediately you can see 2 things. First, my gates are miserable, but second, the DTL has a very large delay going from 0 to 1, and the TTL has a delay too, but it's much smaller. So both of my gates are slow turds right now, but you can already see the problem with the DTL gate that's fixed with the TTL implementation. The turn-on delay of the transistor logic is far smaller than that of the diode transistor logic. We're going to find out why in a minute, but let's first fix our gates so that they at least work at somewhat reasonable speeds. Right now this is 100 kilohertz, so something is clearly not right. There we go, that's a good place to be. The TTL and the DTL are pretty good on the up to down transition, although DTL is slower. There's a huge difference on the down to up. When I saw that at first, I was a bit puzzled. I say, well, let's go back and see where the delay appears. So I'm going to go from here to monitoring here and see if this stage introduces a delay. On my breadboard, I have to move this to the collector of Q2, and I'll do the same on the DTL gate. Alright. And here we start to see some interesting component to the delay. It doesn't go up right away, it stays down and then goes up. So it goes to an intermediate level. But if you look closely at the TTL gate, the same effect is there too. See how it kind of does the same? It has a pedestal before it goes. So I was puzzled by this effect until I found out that I could get rid of it. I'm going to take this wire between Q2 and Q3. Hop! It's gone. And I'm going to do the same over here on the DTL gate. Hop! It's gone too. I have removed this wire on both circuits and isolated Q4 from Q2 over here. So we found by poking around that there is some weird interaction with the totem pole output stage that's fixed by removing the connection between Q2 and Q4. This should already give you a clue of what's going on, but for now I'll let you stew on that. We'll come back to fix it later. The important thing is that we now have a clean Q2 output, and it makes our fundamental problems even more apparent. Our mysterious 0 to 1 transition delay is still there, affecting the diode transistor logic way more than the TTL. Also, once the transitions happen, they are lazy and slow. Now that's a lot less mysterious of a problem, so let's address that first. So when I was studying the circuit, that slow transition caught my eye right away, and that is symptomatic of a transistor that there is some capacitance somewhere and it cannot be discharged fast enough. So there is a usual trick for that, which is to put more current into the circuit and lower your resistors. So I'm going to do just that resistor here and lower it to 470 ohms. So that's the usual trick. When in doubt, make your circuit faster, you drive it harder, you put more current through it, and it will get faster at the expense of power consumption. There we go. Oh, it's much better. By the way, I've invented nothing. If you look at how they made the H gate, which was the fast version of the original TTL, it's the same circuit. They just have lowered the values of all the resistors. And then if you look at the L gate, which is the low power version of the original TTL, they made the resistor higher value, right? And it goes slower. So I fixed that, but it's still not great. Why is there still such a difference between those two? So now we are in a little bit better place. This is 470. Things are a little faster, but there's still a strong turn-off delay here. So let's go and probe over here and see what's happening. I'm prepared, and I put a little poking point here. So right now I'm moving right after the diodes or the inch. And let's look at this. And let's look if there is a delay in the signal that comes out of those two. Not really. This comes out super fast. This is slightly slower, but nowhere close to the delay that we have seen. The delay comes from Q2. It's very different when it's driven by an inch or a 2-emitter transistor compared to when it's driven by a diode circuit. And that's the whole reason why TTL is better than DTL. You can see that the behavior of a transistor is very asymmetric. Goes fairly well from off to on, but it has a real difficult time to come from on to off, and a super extra difficult time in the DTL. This is because of what's called transistor saturation. When the transistor turns on, you start to put carriers into the base, and this will make the transistor more and more conductive, until at one point it's as conductive as it will ever get. Putting more current in the base isn't going to make it any better. This situation is called saturation, when the collector emitter voltage has reached a minimum. When this happens, the collector voltage is lower than the base voltage. So people say that the collector junction is forward biased. Also, that's not a valid explanation, because in a transistor, the PN junction between the collector and the base doesn't behave like a diode at all, so it means absolutely nothing. But what happens is that there is a ton of carriers in the base, and now if you want to get the transistor out of saturation, you have to get all the carriers out of the base before the transistor shuts off. and it takes a while for the transistor to turn off. Sorry guys, I'm foolishly trying to explain this without elevator music and tripping all over myself. But the gist of it is that for a transistor used in a switching application, which usually drive fully on until it's in saturation, the switch off time is much slower than the switch on time. And that's because you have to evacuate the charge buildup in the base. It's a property of bipolar switching transistors that you can easily spot in the spec sheets. T on is much faster than T off. Case in point, the venerable 2N2222, which we are using here. Turn on time 35 nanoseconds. Not bad. But turn off is 250 nanoseconds. It takes forever to get out of saturation. Now, this doesn't happen when the transistor is used in the linear region, say in an amplifier stage. So RF transistors meant to be used in amplifiers can be quoted as having a very high transition frequency, yet they'll be nowhere close to that when used in switching. Case in point again are 2N2222 quoted to a respectable 250 MHz, but with T off at 250 nanoseconds, you'd be lucky to get 2 MHz out of it in a switching application. And that's the huge delay we see in our DTL gate. The genius of the TTL gate is to get around that issue in a very clever way. The TTL circuit is so much better at getting the transistor out of saturation than the DTL. Well, that's because in the DTL, it's just a diode here that doesn't conduct, so the only path for all the charges that are filling the base at saturation is through this 4.7K resistor. And I can't make that 4.7K resistor so much lower or it won't work anymore. However, in the TTL, we don't have a diode junction, we have a transistor. So when the input goes from plus to the ground, suddenly this transistor, which by the way was in saturation, leaves saturation and becomes an active transistor and pulls the charges actively out of the base and brings Q2 out of saturation way faster. So this transistor, which is the key to the TTL, is really used in a very weird way. Q1 behaves neither like the DTL nor like a transistor. It's in between. It has the two modes. When the input A and B are high, there is no current going through the base, then it actually behaves like the DTL circuit. This diode is blocking and this diode is conducting. There's current that passes through Q2 and turns it on. However, as soon as input B or input A goes low, then this transforms into a transistor, so it behaves very differently from this. So as soon as there's a tiny bit of current that goes through input B, it will suck all of the carriers out of Q2 and drive it out of saturation very fast, which is absolutely not happening in the DTL case where it has to go through the resistor. So this thing is used as a diode and as a transistor at the same time. That's what makes it so good. Now you know about transistors and saturation and why a TTL is better than a DTL, but you also will be able to solve the problem that we had before. So let's reconnect the output stage. So I'm reconnecting the output stage. I might do it as well for the DTL gate. Also, there is no hope in the DTL gate. And what's happening is that Q4 cannot get out of saturation. Let me explain that. This transistor is conducting, and this transistor is conducting, and they are both in saturation. This one will be pulled out of saturation by the dual emitter transistor. This one, however, the only thing that pulls it out of saturation is the 1K resistor. So for a while it's conducting, and what I am seeing here is the transistor still conducting, and it's bringing down the voltage through Q3 at the collector. Well, first, why is it happening in this gate? Because I used the wrong transistor. So this was all optimized for the transistor they had. Mine are way bigger, they have way more capacitance. So what I'm going to do, since I have a fairly low resistance here, I can lower this a lot. and this should enable Q4 to get out of saturation way faster. So let's help that poor transistor to get out of saturation and replace that 1K resistor with something way lower. I'm going to try 120. And since I have a transistor of Q2 driving it, I can go fairly low here. It's going to be able to pull it up when it needs to. And yeah, you see it's already much better. I think I could go even a little faster, a little more than that. Let's put 68 ohms. Yeah, it's about perfect. It's about as fast as it will go. So now I don't see if I speed that up. Yeah, it's about the same order of speed than the Q2 getting out of saturation. Let's see if we can help our poor DTL gate the same way. I'll also take the 1K that drives it to ground and replace it with 120. There we go. There we go. So it fixes the DTL too, but the DTL is hopeless. It has Q2 takes so long to get out of saturation that it doesn't help if I hasten Q4 getting out of saturation. So now my gate should be way faster. Let's see how fast we can run it. Okay, now it behaves. Now it goes to 1 megahertz. And we've completely lost the other one, 2, 3, okay. 3 meg, not the fastest ever. You may ask, if you're really astute, a further question. This transistor Q1 also has a saturation. When its inputs are driven low, is going to reach saturation. So how come it has no problem when the input goes back up here? The reason is that it stays in saturation. When the base current goes to 0, it goes instead to the base to collector diode, and all the carriers are evacuated through this. So it doesn't matter because it can switch while staying under saturation. It's really a very unusual use of a transistor. It's first used as a diode, then as a transistor, then it gets into saturation, but it's not a problem because when you switch from the transistor mode to the diode mode, it doesn't matter that it's saturated. So it's somewhat genius and somewhat unobvious, so much unobvious that it's not described in the patent. So I'm not sure the guy that wrote the patent at TRW understood exactly what was happening. That's why it's usually not explained correctly, because it's very unobvious. Now, is there a way to make it even better? Yes, you can. And I'm going to transform my TTL gate into a Schottky, an LS gate, by putting a Schottky diode. And the way to do this is to basically prevent the transistor from going into saturation ever. And in order to do that, it's another genius trick. You put a Schottky diode between the base and the collector. Let me demonstrate. I had a Schottky diode somewhere. Here it is. So a Schottky diode, this little guy, a diode that's A, very fast, and B, has a very low voltage drop across it, 0.2 volts instead of 0.6 volt for a silicon diode. I put it between the base and the collector and look at what happened. Now my transistor is way faster getting out of saturation. And the reason it does that is that the diode prevents the transistor from going too deep of saturation. It has only 0.2 volts. Saturation is very weird. When it happens, the voltage of the base is higher than the voltage of the collector. But one way to prevent it from reaching that point is to put this diode, and this will limit the differential between the base and the collector to get too much bias forward to 0.2 volts. And it will never go very deep into saturation. Basically, it steals electrons from the base. It only ever goes deep into saturation, it just goes a little bit, so you extract the maximum out of the transistor. The TTL S gates were made first with Schottky, and then they did the LS, the low power version of it. For the last bit, let's put better transistors. It's a 2N2222, it's not the best, but really here what matters is how fast it goes out of saturation. So here I have an 800 megahertz transistor, but once again it's not going to make a huge difference because it's just a tiny bit faster at going out of saturation. So it's, you see that's helped already. If I change this one, this is going to make my transition up faster, it should. And if I change this one, it might make my transition down faster. Whip. There we go. A little better gate by improving the transistors. Let's go faster. 4 megahertz, 5 megahertz. Okay, so now we have a decent gate with decent transistors and a Schottky diode. I can run it to 10 megahertz and then it becomes a little iffy. But it looks like a gate at 10 megahertz. So here you go. This is the genius of the TTL gate. And then they kept improving on the thing, and they went with more and more complex stuff. And at the end it's completely incomprehensible, but they went after everything they could refine by putting more transistors and diode in the thing. Alright, well, I hope you've learned something. I did. Thanks to the inch, we finally are able to understand the good old TTL circuit that's still with us today in a much refined form.